So, we have seen how to apply the inverse CDF method for continuous random variables. How can we apply this method to discrete random variables? It turns out that this method of inverse CDF transformation is applicable to discrete random variables as well. Let's suppose that x is a discrete random variable with finite or countably infinite sample space omega. So the possible outcomes of x include x1, etc., all the way to I minus 1, xi, xi plus 1, etc. And each of these outcomes are ordered. In other words, for any I, xi minus 1 is less than xi, which is less than xi plus 1. In this case, the xi's, which are the possible outcomes, so the possible values that the discrete random variable x can take, will be the discontinuity points of the CDF fx. For example, CDF might look like this, which looks like a step function, where it jumps at each of the possible outcomes xi's. Further, you can see that in this case, the probability that an outcome xi occurs is equal to the CDF at xi minus the CDF at xi minus 1. So how can we apply the inverse CDF method to discrete random variables? Actually, the procedures are quite similar. In step 1, we want to define a function hu, where u takes values between 0 and 1, such that hu is equal to xi if the CDF evaluated as xi minus 1 is less than u, which is less than the CDF evaluated at xi. In other words, for a u value between 0 and 1, if it lies just between fx of xi minus 1 and fx of xxi, then we set hu equal to xi. This is a replacement of the inverse function earlier for the continuous random variables. Step 2 and 3 are quite similar to before. So in step 2, we want to draw random uniform samples from 1 to n. And then in steps 3, we perform the transformation. We set the jth x equal to h applied to u of x for each of the possible j's between 1 to n, where n is the number of samples we want to draw. The rationale behind this procedure is quite similar to the inverse CDF method for the continuous case. You can easily verify that the probability that an x obtained this way takes the value of xi is equal to the probability that that a uniform random variable is between fx of i minus 1 and fx of xi, and we know that this under the uniform CDF is equal to fx of xi minus fx of xi minus 1. And that's equal to the probability that x is equal to xi under the distribution fx.